So one important skill that you'll need to develop throughout the semester is looking at limiting cases. And what do I mean by limiting cases? Well, in many cases, we're going to calculate, some functional form. So let's imagine, for this example here, we've got some kind of a ring of charge. Okay, so we've got this ring of radius r, and there's some kind of charge distributed along it. A charge q that's distributed uniformly over it. And let's say we obtain some function for the electric field at some position away from the center of the ring. So let's say if we go up and down the z-axis here, we have basically this functional form, and this is exact, that E sub z is equal to k times q times z over the square over z squared plus r squared to the 3/2. Okay, you don't need to know where this comes from. For the time being, let's just imagine it's just some arbitrary function. Okay, but the function looks a little bit messy. I mean, there's this z here, there are these z squareds here, and there's all this stuff raised to the 3/2. So, oftentimes you look at this function and you may not be able to get a really good intuitive feel for what this actually means. So we can ask a question, which is, what is the approximate form that this exact function here takes in two limits? Let's say we can take it at the limit of z is much, much less than the radius of the ring r. So it's, let's say, very, very close over here. Or z is much, much larger than the radius of the ring. So it would be, way, way far away. Okay? And when I mean approximate, I don't mean, what is the exact value of E sub z at 0, for instance. That's the extreme limit of z much, much less than r. So it's at 0. You can see here from this function that basically I plug in 0, I get a 0 here, and the answer is 0. You can also see, hopefully, that if you go very, very far away, if z is really big here, that basically this term dominates over the top, and it also goes to 0. That's not really what I mean by the limiting case. What I mean is sort of how is it trending as it's, getting really close to 0 or getting really close to infinity. I still want to know what the functional form is, and hopefully this thing simplifies to something a little bit more, more informative just by looking at, we can get some sort of feel for how E sub z is behaving. So first of all, let's take the situation of, let's say, z much, much bigger than r. Okay, so this point is really, really far away from the ring. And again, we have, I'll just rewrite this really quickly. And you'll notice I'm pulling the k and q out in front. And there's a reason for that. The reason is as follows. KQ is a constant, right? So in this expression here, the only thing we're going to be worrying about is how z varies. This KQ term is just a multiplicative factor in front, right? It doesn't vary as a function of z. So basically, when we want to know how things are trending, we can just ignore this for the time being. So we can just concentrate our attention on the fraction. All right. So, we have basically this numerator here. So that's just z. That's pretty clear. If z here is much, much bigger than r, we can ask, well, how will this thing behave, right? So we can look at the thing inside the bracket. So if z is much, much bigger than r, then z squared, so if r was 1 and z was 100, you can kind of convince yourself that this is really just pretty close to z squared. So the r squared is kind of negligible. If, so for instance, if I said that z was 100 and r was 1, then z squared plus r squared would be, if you just plug this into your calculator, it would be 10,001. And we know that z squared is 10,000. So you can see, to much better than a percent, z squared and z squared plus r squared are almost the same thing. So what we can do then is just say, okay, well, in that case, if z is really much bigger than r, then, I have this kq, which I'm not really concerned about. What I'll have is something that looks like this. Z on top, and this thing on the bottom will look basically like z squared. To the 3/2, right? So this is approximately. So then z squared to the 3/2 is just z cubed. So I'll get something that looks like this. KQ. So the curly, the squiggly equals is basically just approximately, and it's going to look like 1 over z squared. For those of you that have had some experience with electrostatics, you know that the electric field from a point charge goes as kq over r squared. So what we're saying here is that when we get really, really far away from the ring, we can't really tell it's a ring anymore. It's just a speck, right? It looks just like a point charge. So that kind of makes sense. When we get really far away, the sort of shape of that ring doesn't really matter anymore. It's just some little dot with a charge q. And so that kind of makes intuitive sense. So again, we can now kind of plug in numbers to see how all this works. So like I said, for this, let's take let's take a couple numbers. So we'll set r is always equal to 1 meter. And we'll say z is 100 meters. So if I evaluated the exact fraction, z over z squared plus r squared, to the 3/2, and I substituted in these values, the exact form would give me 0.00009985, and the approximate expression, which is basically 1 over z squared, would give me 0.0001. So basically these are, very, very close. So basically these are, to within better than 1% accurate. Okay. And of course, if I went to something even, to z even bigger, like 1,000 meters, then this would get even closer. So you can see that this is a really good approximation. And what I usually like to do is, oftentimes I'll just punch in numbers just to make sure that I've done the calculation right. So now we can look at the opposite limit. So we can look at z much, much less than r. So in the case that z is much, much less than r, again we have E sub z is equal to kq z over z squared plus r squared to the 3/2. And so what I'm going to do here is I'm just going to rewrite this. I'm not going to do any approximations yet, but rewriting it oftentimes sort of helps us understand what, how things should look. So I'm going to pull it, so z is still on top here. I'm going to factor out a factor of z cubed out, okay? And what that will leave us with inside the bracket is something that looks like this. All right. So in that case, then we can look again at the stuff inside the bracket. So 1, we have this thing that's 1 plus z squared over r squared. And so if z is much, much less than r, then basically this is going to look pretty close to just 1. Okay, this term will get really, really small. So again, like I mentioned earlier, so if let's say z was 0.01 meters and r was 1 meter, what would we get? So if we actually calculated it out, so 1 plus 0.01 over 1 squared, that would give us 1.0001, which is pretty close to just 1. Okay? So in this case, then we can basically say, well, the stuff inside that bracket, it's really close to 1 when z is much, much less than r. So in that case, it's not a bad approximation just to substitute this by 1. So we'll get an expression that looks like this. KQ z over r. All right. And so what we can see now is, going from this expression here, where it's not entirely clear maybe how z will behave when z is much less than r, you can see now, okay, well, after we sort of looked at this quantity here and so seeing that it's really close to 1, what we can see now is that, this looks like it's exponentiated, it's not, is that basically it looks like it's going linearly, right? So as we get very close to the origin, when z is much, much less than r, basically the electric field is going linearly. So it's going just, this is just a constant here, kq over r, and then multiplied by z. And again, what we can do is we can compare. So the exact form versus the approximate, which means it's going sort of proportional to z. And again, let's use the values of z is 0.01 meters and r is equal to 1 meter. So we're actually going to plug things in. The exact form would give us something that looks like this. It would be 0.009999. And the approximate form would give us 0.01, right? So you can see how close these are. So you can basically now see that, to a really, really good approximation, as we get close to the origin, the electric field is basically just going linearly with z. And that approximation is good to, much better than 0.1%, okay? So again, what I oftentimes like to do, if you aren't comfortable with this step here, one thing you can typically do is just to basically do the calculation, just plug in some numbers with your calculator, and you can kind of see how things are trending, right? So for instance, if I didn't know to simplify this, but I just started with this exact form here, and I just started punching in numbers where, let's say I started with, I kept r is equal to 1 meter, but I used 0.01 meters here, or maybe and then I used 0.02 or 0.03. I could basically see how E sub z would be changing as I change this by some known value. And then I can basically say, oh, it's going linearly, or I might be able to tell, oh, it's going quadratically, or as the third power or something like that. But it's basically something that you can, just by using your calculator, get a good feeling for how things are, A, how things are trending, and B, how good your approximation actually is. So finally, I will just mention this briefly, although I will not cover it, is that there's a more formal way of doing this, which is basically using a Taylor series expansion. We may see it once or twice in the class, but in general, I think that for the purposes of most of what you'll be doing, I think this sort of just, doing this, looking at these expressions and sort of evaluating them by sort of observation, if you will, is probably an easier way of doing it. So the Taylor series expansion is probably something you've learned in your calculus class. So it turns out in physics it's actually incredibly useful. So what you can basically do is if your function has some sort of functional form, you can basically expand about some point in terms of various powers. So you can basically fit your function by some series of polynomials. And to actually get what prefactors are in front of your polynomials, you basically take the first or second or third derivatives, etc., around that point. But that's a little bit beyond the scope of this class, although we might see it in one or two problem set questions here and there. And that's something that you can just look up in your calculus textbook or online.